Okay, thanks a lot. Thanks a lot for the opportunity to speak here. So this mini course is going to focus on Artin groups, what they are, why we care about them, how to study them, and it's going to be the opportunity to see how to use groups acting on non-positively curved spaces to derive some properties of these groups. So maybe to get started, so I guess I'll start on this side. So let's talk a bit about Artin groups. So Artin groups and their kind of relative Coxeter groups are defined using what's called a presentation graph. So a presentation graph is a finite simplicial graph gamma such that every edge comes with a label, say between A and B, has a label MAB, which is an integer at least 2. And once you have this data, you can define some groups from it. So the first one we're going to be defining is the Artin group A gamma, which is the group given by the following presentation. So the generators are going to be the vertices of your graph, so V of gamma. And you're going to add a relation every time you see an edge between two generators, and the relation is going to be some sort of generalized braid relation. So the product AB, AB, etc. is equal to the product BA, BA, etc. with MAB letters on each side for every edge AB in gamma. So that's your presentation of your Artin group. There's another group that we can associate to this presentation graph, which is the Coxeter group W gamma, which is given by the same relations, but you further require that every generator has now order 2. So A square is equal to 1 for all. There's a map that goes from A gamma to W gamma just by adding those relations. So what are some examples of Artin groups? So what are some examples? You've probably seen Artin groups in one form or another. So for instance, if gamma is discrete, so there's no edge at all, so we got our generators indexed by B gamma and no relation. So in that case, A gamma is a free group. Another type of example that you have probably seen a class of groups that people really care about and have studied extensively. So if all labels are equal to 2, so it means that the only relations that we are adding are that certain generators are going to commute with one another. Not all of them, but some of them. In that case, what we get is what we call right-angled Artin groups. Those ones are very popular with their very nice cat-zero cubical structure. Maybe another example, a bit different. If you take gamma, which is the following triangle with edges 3, 3, and 3. So in that case, the Coxeter group that we get is isomorphic, the symmetric group S4, and the Artin group is isomorphic to the braid group E4. So maybe this is to illustrate that. How do you see on this graph that this Coxeter group is going to be S4? This is going to correspond to, so this generator is going to correspond to the transposition 1, 2, this 1, 2, 3, this 1, 3, 4. And now you recognize some relations are quite standard. These two transpositions have disjoint support, so they commute, which is encoded by this edge with the label 2. And for adjacent transpositions, you get a braid relation encoded by this edge here. So, so these are examples of the Artin groups. So we'd like to understand their properties, and especially kind of comparing them with Coxeter groups, which are much better understood. So Coxeter groups have a very nice structure. Many questions about them are now understood. Their algebraic properties, their geometry, they're known to be cat zero, for instance. By contrast, for Artin groups, essentially everything is unknown in full generality. So just to give you like maybe 2 examples, so many open problems for Artin groups. For instance, so are Artin groups torsion free? So you would expect that, like, a very basic thing that you would like to understand when you're given like a group and a group presentation is kind of understanding whether or not a group has torsion. This is not known in general. And something even more basic, like, can you work with this presentation? So do Artin groups a solvable world problem? And that's known as well. It's kind of interesting when you see how little is known about Artin groups in general. So fortunately, people have been able to answer some of these questions, at least for some subclasses, by adding like further restrictions on the type of Artin groups so that we get X-class structure. So some better understood families, and we're going to focus on some of them in this mini course. The first one is called family of spherical type. That's when the underlying Coxeter group is finite. I guess I mentioned one earlier, so RADs are very well understood. Another one, which is the family of large type Artin groups. That's when all labels are at least 3. So you forbid commuting relations in your presentation. Sorry? Oops, sorry, it's at least 3. Thank you. So you forbid commuting relations. And there are variations of this. So XL type is when it's at least 4. Extra large is when it's at least 5. So you get the idea of the pattern. So these ones are quite well understood as well. And these ones fit in a larger family called 2-dimensional Artin groups, which is a family of Artin groups whenever you have a triangle A, B, C in your graph, you have the condition that the sum of the inverses of the labels is at most 1. And we'll go back to this condition a bit later. So that's the families of Artin. Yeah, sorry, yes. Yeah.
So you referred to the Coxeter group as underlying. Is there a way that I should think of the Coxeter group as some kind of like essential structural subgroup of the Artin group?
So it's not a subgroup, it's a quotient. It's not clear how essential it is. For instance, here's an open question. If you have 2 isomorphic Artin groups, do they have isomorphic Coxeter groups? So, you know, like Artin groups are given to you by means of a graph, but there could be two different graphs that give you the same Artin group or the same Coxeter group. And this is linked to like a very famous open problems called the isomorphism problem for Coxeter or Artin groups. So it's not true in general that an Artin group is characterized by a graph. So in particular, it's not clear that the Coxeter quotient is kind of naturally associated to your Artin group in kind of algebraic sense. It's associated when you kind of fix a presentation, so a presentation graph, but otherwise it's not clear. Does that answer your question?
Yeah.
Okay. Other questions? Yeah, I should have said if you have a question, just maybe shout because I might not see your hand. Okay. So I mentioned some algebraic questions about torsion freeness and all that, but we're doing geometric group theory, so we like geometry. And a natural question to ask is what is the geometry of these groups? So I mentioned that Coxeter groups are cat zero, and a general theme is that we expect Artin groups to have the same sort of nice properties as Coxeter groups. In particular, here's a question: are Artin groups cat zero? Or okay, cat zero is it's kind of a very famous notion of non-positive curvature, but it's not very flexible. It's very hard to check in general, or just say or non-positively curved in any reasonable sense. So there have been lots of alternative notions of non-positive curvature, systolicity, hailiness, bioautomaticity, and things like that. Essentially, are Artin groups one of these? Either works. And again, it's not known in general. There are some classes that are known to be non-positively curved. We're not going to focus on that, but I'm just going to briefly mention some. So I talked about large type Artin groups. Those ones are known, for instance, to be systolic, which is kind of a combinatorial notion of non-positive curvature, and that's a result due to Wang and Coxeter. And if you want to ask him more about this. Brads are cat zero cubicles. Those ones have a very nice geometry. Spherical type also have a nice non-positively curved geometry. They're called heli. That's also due to Jing Yong and Damian Ozaida. So in this mini course, we're going to focus on two-dimensional Artin groups. So there is kind of a notion of non-positive curvature as well. It's called metric systolicity, which is again due to Damian and Jing. But instead of focusing on the geometric properties, I'm going to try to focus on kind of avatars of non-positive curvature. Since we don't have a nice kind of universal notion of non-positive curvature, can we at least try to see what sort of properties we expect from non-positively curved groups in general, and try to prove this property. And the property that I'm quite fond of and that we're going to focus on in this mini course is called the Tits Alternative. So there's a folklore conjecture. Cat zero groups satisfy the Tits Alternative, i.e. every finitely generated subgroup either contains a free group or is virtually solvable. So it's a kind of striking dichotomy at the level of subgroups. They're either very big, they contain a free subgroup, or they're very small in a sense, they're virtually solvable. So there are also groups that are known to satisfy this. So linear groups were the first examples due to Tits. And since then, we've come to expect that so not only cat zero groups, but any sense of non-positively curved group should satisfy the Tits alternative. Right. So in particular, since we expect Artin groups to be non-positively curved, we should expect them to satisfy the Tits alternative. So the natural follow-up question is which Artin groups satisfy the Tits alternative? So there's already some results. So let's go through some of this list. So that in the spherical type, so spherical type Artin groups are known to be linear and linear over R or C. And so linear groups do satisfy the alternative, the Tits alternative. So these ones do, so because they're linear. And so that's due to Cohen and Wales, and independently by Bigne. What else? Rags, right? So rags have a very nice geometry. They're cat zero cubical, and this is due to and the fact that cat zero cubical groups satisfy the Tits alternative is due to Sagiev and Wise. And right, there were some earlier examples. So we're going to focus on two-dimensional Artin groups in this mini course. One particular subclass that was already known was the class of XL type Artin group. And this was due to myself and Piotr Psztycki. And I was using a very nice action of these groups on some hyperbolic space. And this course is going to focus on following results. I'm gonna try to give you a survey of this alternative for all two-dimensional Artin groups. Two-dimensional Artin groups satisfy a strong form of the Tits alternative. Every subgroup, a subgroup of A gamma, either contains F2 or is virtually abelian of rank at most 2. So indeed, it's a very strong dichotomy between very big subgroups or very small subgroups. And the idea, what's going to be our strategy to do that, the strategy is going to try to use the action of Artin groups in some nice non-positively curved space, actually in some nice cat zero space, to try to study the subgroups of a given Artin group. So the strategy study the action of A gamma on some nice cat zero complex. Okay, yes.
Did you drop the finitely generated requirement?
Yes, actually, we're not going to need the finitely generated. There's going to be any subgroup. There are a few cases where the Tits alternative can be proved in such a strong form. We don't need the finite generation. I think actually in the SL type, if I remember correctly, that was also for any subgroup. Yeah, so that does happen for quite a few groups. Other questions? Yeah.
Perhaps maybe a more elementary or fundamental question. What was the inspiration for this two-dimensional Artin group definition? Like, what were you trying to capture exactly with this?
Right. So that's a very good question. It's actually related to what I'm about to introduce here, which is that nice complex that we want to study. In particular, at some point, you need to show that your complex is cat zero, right? Showing that something is cat zero is extremely hard in general. There are essentially only two classes of spaces where showing cat zero-ness is kind of reasonable: two-dimensional spaces and cat zero cubical space. I'll go over that a bit later. And the two-dimensional Artin groups are exactly the ones where this complex turns out to be two-dimensional, so for which it's reasonable to check that they are cat zero. There's another kind of way to think about two-dimensional Artin groups. Because of some very famous open problem called the K-pi1 conjecture for Artin groups, the two-dimensional Artin groups are exactly the Artin groups that have. Let's maybe whose maximal Zn is a Z2. So it's kind of a way to quantify the kind of abelian dimension of the groups, the maximal free abelian subgroup. And the two-dimensional ones are exactly the ones where Z2 is the maximal dimension of an abelian. Okay. Other questions? Okay, so let's introduce the main protagonist. So the complex we're going to be focusing on is called the modified, and I'm going to drop this adjective very soon. The modified building. So this complex is going to be. Oops, I've dropped the mic again. This complex is going to be defined out of certain subgroups of an Artin group. So I'm going to start by defining those ones. We've got our Artin group A gamma for with generating set, which we're going to call S. So the set of vertices of gamma. So for S prime, a subset of S, we can the subgroup generated by S prime is called a standard parabolic subgroup. That's going to be the key type of subgroup, and any conjugate such a subgroup is called a parabolic. So essentially, I've started from my presentation. I'm just looking at certain generators, and I look at what they generate. So if you give me an arbitrary representation, it's generally very hard to understand the subgroup generated by a subfamily of generators. Thankfully, in the case of Artin groups, everything works reasonably well. There's a very nice result due to van der Leck. Tells us that standard parabolic subgroups are essentially what you would expect or hope for. So again, so the same setting, we take S prime, a subset of S, and we look at gamma prime, the subgraph of gamma induced by S prime. The vertex set is S prime, and whenever two vertices of S prime are connected by an edge, that edge is also in gamma prime. Okay, then the standard parabolic subgroup, so the subgroup generated by S prime, is actually isomorphic to the Artin group associated to gamma prime. So you restrict, you no longer have a but if you have, say, like a triangular Artin group, and you look at just these two generators, then actually the subgroup they generate is the Artin group that you get by just focusing on that particular subgraph. There's another result that is quite useful. So from now on, I'm going to use that notation instead of this one. Also, so standard parabolic subgroups intersect the way you expect. If you take two standard parabolic subgroups, they intersect along the parabolic subgroup corresponding to the intersection of their subgraphs. So essentially, for parabolic subgroups, everything kind of works nicely. So we can now introduce the complex being kind of teasing out here. It's called the Deligne complex, and it's the modified Deligne complex. It's due to Charney and Davis. So the Deligne complex, modified Deligne complex, but I think by now most people call it the Deligne complex. We're just going to drop the modified adjective. Is defined as follows. The vertices are in bijection with the cosets of standard parabolic subgroups of the G A gamma prime, where A gamma prime is of spherical type. So the cosets of standard parabolic subgroups where the associated Coxeter group is finite. And for the simplices, so whenever the chain of inclusions, the form gamma 0, strict inclusion gamma 1, etc. Gamma k is gamma of full subgraphs. Then we put a k simplex G A gamma 0 all the way up to G A gamma k. Let me say, so whenever this, and also I need an element of my group. So I get this these simplices. So that defines a essential complex. I'm going to want an action of my group on it, so I'm going to define it now. A gamma acts on the Deligne complex, which will give a notation B gamma by left multiplication on left cosines. Okay, I'm going to draw some examples. It's a bit hard when you find like that. By the way, so show of hands. Who here is familiar with Coxeter groups and maybe the notion of the Davis complex associated with a Coxeter group? Okay, so you probably recognize, or at least this definition looks familiar. For a Coxeter group, you should do exactly the same thing. So the same vertices, cosets of standard parabolic subgroups when the corresponding parabolic subgroup is finite. Same simplices, same action. What you've just defined is the Davis complex of your Coxeter group and the corresponding action of the Coxeter group. So the Deligne complex is in a sense kind of the analog in the Artin world of the Davis complex in the Coxeter world. Okay. Very good. So actually, is there? Okay, there's no time. So I need to stop at 15 past, right? Okay. Sorry? At most 20 past. Good. Oh, there's another one. Oh, there's three boards. Okay, so that's a massive reveal. Okay, let's try that then. So, are there questions about this or no? So examples in the two-dimensional world. So what are the standard parabolic subgroups of spherical type when we have the two-dimensional Artin groups? So standard subgroups are of three type. So essentially the ones where what subgraph is allowed for A gamma prime is the empty subgraph, in which case what you get is just the trivial subgroup. And so you're looking at the G A gamma prime, and those ones are going to be called type 0 vertices. There's also the case of a single vertex, in which case what you get is an infinite type A subgroup, and the corresponding Coxeter group is Z2, which is finite. And those ones are going to give you the type 1 vertices. And finally, gamma prime, which is allowed to be a single edge between A and B with the label M, in which case A gamma prime is what's called a dihedral Artin group. And the corresponding Coxeter group is what's called a dihedral group, which has order 2n. So it's also a finite Coxeter group. So these ones are called type 2. Why is there nothing else? Well, this is where the kind of definition of two-dimensional comes in. If A, B, C are three generators of B gamma, the fact that the sum of the inverses of the labels is at most 1, this is the condition that implies that the corresponding Coxeter group ABC is infinite. So when you look at a Coxeter group generated by 3 elements, there's a complete understanding of what happens if that sum is strictly bigger than 1. You have a finite Coxeter group that corresponds to a tiling of the sphere. If it's equal to 1, you get a group that acts geometrically on the Euclidean plane. If it's strictly less than 1, it acts geometrically on the hyperbolic plane. So this condition was is the reason why we don't have to look at any other type of standard parabolic subgroup here, because the corresponding A gamma prime is not going to be of spherical type. So these are all the vertices in our Deligne complex, and in particular, D gamma is a 2-dimensional simplicial complex, and triangles are of the form G A empty, G a generator A, and G A and 2 generators AB. AB is an edge of gamma. So let's look at a concrete example. That I'm going to need those 3 lectures to really understand how the boards work. Yeah. Sorry. All right. Okay. Thanks. Let's look at one example. So I'm going to look at gamma, which is the triangle 3, 3, 3. So that corresponds to a 2-dimensional Artin group, because there's only one triangle in it, and the sum of the inverses is exactly equal to 1. So the condition is satisfied. So in particular, if I look at this picture here, I've got my 3 types of standard parabolic subgroups. So I'm going to draw a portion of the Deligne complex that corresponds to the cosets for G is equal to the identity. So I'm just going to look at a small piece. So let's draw that. So I've got the one corresponding to the empty subgraph. So AMT. I've got the one corresponding to each generator. I also have the vertices corresponding to the one corresponding to edges, and I'm drawing them in that weird way for a very specific reason. That's going to be clear in a second. So that's the vertices corresponding to G is equal to the identity. Now I need to put the edges, and the edges correspond in particular to the inclusion of the parabolic subgroup. And here we see that we have the inclusions like this. Essentially, what I'm seeing here is a divided, so the Weissenbeck division of a triangle. And so I can really think of it as a single triangle subdivided. So that was for G is equal to 1. And so I'm going to call this thing, say, K gamma. So if I try to look at draw a bigger portion of the Deligne complex, so here I've got K gamma. What happens if I apply the element A to this? So I'm translating this tile by the element A. So because A belongs to these parabolic subgroups here, this tile is going to be glued to the previous one along that edge. So what I'm going to see appearing here is A gamma. So if I do A squared, I have the same feature appearing. So what I'm going to see here is something like this. That's A squared K gamma. And again, so what I'm seeing appearing is a complex that is highly non-locally finite, where the various groups generated by the generators act by essentially rotating those triangles. It's a very complicated space However, there are a few nice things. So A gamma acts on D gamma co-compactly. That's almost, that's a direct consequence of the definition. The vertices, the simplices corresponding to up to the action of the group to the chains of inclusions of subgraphs of gamma, because gamma is finite. There are only finitely many such possible inclusions, so only finitely many possible orbits of elements of simplices. So the action is co-compact. Something that's maybe less clear from the definition. D gamma is simply connected, and the key results that we're going to need. The key result that we're going to need is a result due to Charney and Davis, which is that if A gamma is a two-dimensional Artin group, there is piecewise Euclidean metric on D gamma on the Deligne complex, such that D gamma is cat 0, and A gamma acts on it by isometries. And that's really going to be our key tool now for a two-dimensional Artin group. For instance, you can think of essentially the triangles 3, 3, 3 is a good example to have in mind. You can forget all other types of two-dimensional Artin groups. Everything that we're going to do, you can try to visualize it on this particular example. So this complex here now will be endowed with a cat 0 metric. So maybe I've got maybe 1 minute or 2 minutes left, and I'll finish here. How do you put a metric on a simplicial complex? So at the moment, the Deligne complex is it's a combinatorial object. It's a bunch of vertices and some data about which vertices are connected by an edge or a simplex. There is a way to put metrics on an arbitrary simplicial complex, which is kind of analogous to what you've done, what you know, I'm sure, for graphs. So presumably, when you think of the Kelly graph, you think of it as a metric graph, and the way you do that is by saying, I'm going to impose that every edge has length 1, and then I'm going to consider the path metric, right? And you can do something completely similar for a simplicial complex by defining what's called a piecewise Euclidean structure, which is essentially identify each simplex with a simplex in the Euclidean space, in some Euclidean space En, in a compatible way, and take the quotient metric, which is essentially you do the natural thing you'd like to do. Once you've identified every triangle with some triangle is a E2, so now each triangle comes with a metric, right? You're really thinking those ones are like Euclidean equilateral triangles or a right-angled triangle here. So whenever you have 2 points inside a triangle, you know how to define their distance. And now what you want to do is, if you have points that are further away, then consider like strings of points. And the way you're going to measure the length of that string is by adding those bits of distances when you travel inside a given triangle. And the distance between x and y is going to be the nth of the length of those strings. So it's the same thing that you do. The same thing that you do in a graph. That's exactly how you define the path metric in a graph, but generalized to a high-dimensional complex. So that's exactly what they do in that particular case. They define a piecewise Euclidean structure here. For that particular example, 3, 3, 3, you can take every triangle appearing here, so the big pink triangle, to be an equilateral triangle. So you can take all these smaller ones here, the ones that really come from the Deligne complex, we have angles pi/2, pi/6, and pi over 3, and that's going to give you the Euclidean structure that you want. Of course, the hard thing is how do you check that this gives you something that is cat 0? I'll not going to have time to mention this now. Maybe I'll mention that briefly at the start of the recitation tomorrow. But the key thing is in dimension 2, there's a very simple criterion to check that something is cat 0 called the Gromov-Link criterion. So we'll see that tomorrow. So I'll stop here for now. Thanks.
So this is simply connected. Is it contractible by sort of contracting a whole long leaves or whatever I mean?
Yes, you can try to. Right. So maybe it's easier to see it like even for the Davis complex. For that case, the Davis complex is just the tiling of the Euclidean plane by equilateral triangles. Right. So maybe a simpler thing. And if you take a loop starting, say, at this point here, you're going to be able to kind of read or deform it onto something that only visits edges of this type. And the subgraph that this defines is actually the Cayley graph. Okay, so you can see the Cayley graph inside the Davis complex, and you can see the Cayley graph of A gamma inside the Deligne complex. And using that and the fact that the relations that appear in representation are going to bound disks also in the Deligne complex, you're going to be able to show that it's connected. Yes, there are other ways to, if you know the theory of complexes of groups, there's another. There are other ways to think about it, but it's maybe like the more geometric and kind of hands-on way to see it.
More questions?
Yeah.
So I think I missed it. Did you say that you can take like any Euclidean, like piecewise Euclidean, you can fit your triangle however you want, as long as it's compatible, and you get a triangle or you have to like. So
not okay. So there are two things. So the first thing is, do you get a metric? It's not always the case. So to get a metric, you need to take, or at least to guarantee that you have a metric, you need to take only finitely many kind of isometry types of, say, triangles in the two-dimensional case, which is going to be the case here because essentially you've got this finitely many triangles because your graph gamma is finite. So once you pick those ones, it's just going to determine all the other metrics on the other ones. So that is going to guarantee that you get a metric. So this becomes a geodesic metric space. But then there's the question of being cat 0, and this is not related to the piecewise Euclidean structure. The piecewise Euclidean structure just tells you get a metric space. Then to check that you're cat 0, you're going to need something else, and that's where the Gromov's link condition get very useful. And I'll mention that tomorrow at the start of the recitation.
Here I will pass on the homework bits and the bank again.